Hey everyone, Morgan here. So we're looking at page 5 of the Kinetics lectures for AP Chem, and we're going back into the concept of graphical data, which I absolutely love. Now, we've talked mostly about first, second, and zeroth order reactions. So if we collect laboratory data, very likely from something like a spectrophotometer, we can create plots of concentration versus time for all three of these. And when I do that, for a first order, I get something that looks kind of like that. For a second order, pretty similar. And for the zeroth order, something that looks like this. Now, it's important to know that I absolutely love when I get a straight line. That works wonders for me. Okay? But what type of plot would give me a straight line for these two? See, this I can write, y equals mx plus b equations for. Well, when you play around with the data, what you find out is that the natural log of the concentration versus time for a first order reaction gives you a straight line. Now when it's a second order, it's the reciprocal of the concentration versus time, but now the line goes up, which I think would make sense to most people because you're taking reciprocal. So with these three straight lines, I can now write something in the form of y equals mx plus b. Most of you know I have a pretty unhealthy obsession with the slope-intercept form. I think the judge referred to it as stalking, but that's a story for another day. Now, for a first order, that means the equation is going to be the natural log of the concentration, we'll call it A, is equal to minus kT plus the natural log of the original concentration of A, which is where this would hit the y-intercept. For a second order, 1 over the concentration of A equals kT plus 1 over A naught. And then for the zeroth order, it's simply the concentration of A equals minus kT plus the concentration of A naught. So those are great slope-intercept forms, and they get a name. We can now call them the integrated rate law. Now the typical differential rate law that you know for a first order reaction is R equals K times A. For a second order, it's R equals K times A squared. And then for the zeroth order, it's just simply a constant, R equals K. Now, this right here is the integrated rate law for the first order, this right there for the second order, and that for the zeroth. In this case, the slope of this graph is equal to the negative rate constant. For a second order, it is the rate constant, and there that's the negative rate constant. And we put the negative signs because, the plots are going down, but rate constants need to be positive numbers. So if they're not positive numbers, they're not of much use to us. Now, on the next page, what we're going to see is that the half-life of a first order reaction is equal to 0.693 over K. For a second order, it's 1 divided by K times A naught. And for a zeroth order, it is A naught divided by 2K. And we'll develop those on our next page. All right, this is Morgan signing off.